Hello and welcome. I'm so glad you're here with me tonight. Before we begin this gentle journey into the heart of the stars, I want you to find a comfortable position. Let your breathing slow. We are going to explore something truly beautiful together. Right now, as you listen to these words, somewhere in the vast darkness of space, a star is being born. Not with violence or chaos, but with a quiet, patient gathering. Hydrogen atoms drifting alone for millions of years are finally coming home. They're pulling together, drawn by an invisible force, beginning a transformation that will light up the cosmos for billions of years to come. This moment happening right now, across the universe, holds the secret to everything you see, everything you touch, and even the atoms that make up your own body. If you're finding peace in these quiet wonders of the universe, I'd be grateful if you'd subscribe and leave a like. It helps others discover these calm explorations of science, and it means the world to me. Thank you. Now, let's begin at the very beginning. Let's witness how stars are born. Imagine, if you will, a region of space so vast it would take light 5 years to cross it. This isn't empty space, though it might seem that way to our eyes. It's a nebula, a cloud of gas and dust, floating silently between the stars. The Orion Nebula, visible even to the naked eye on a clear winter night, is one of these stellar nurseries. It lies about 350 light-years from Earth, close enough that we can watch the birth of stars in remarkable detail. When you look at Orion's sword hanging below his belt, you're seeing a maternity ward of the cosmos. These nebulae are patient places. For millions of years, they simply exist. They're atoms drifting in the cosmic dark. The density is almost incomprehensible to us. In the densest parts of these clouds, you might find about 1,000 atoms in every cubic centimeter. That sounds like a lot, perhaps. But compare it to the air you're breathing right now, which contains about 10 billion atoms in that same space. The nebula is, by our standards, a near-perfect vacuum. And yet, this is where magic begins. Something disturbs the cloud. Perhaps a nearby star explodes in a supernova, sending shock waves rippling through space. Perhaps two galaxies pass close to each other, their gravitational dance stirring the cosmic gas. Or perhaps, in the patient mathematics of gravity, the cloud simply reaches a critical size. Whatever the trigger, certain regions within the nebula begin to collapse. Gravity, that gentlest and weakest of nature's forces, begins its slow, inexorable work. At first, the collapse is almost imperceptibly slow. A volume of gas the size of our entire solar system might contract by just a few kilometers over 1,000 years. But gravity is patient. As the cloud contracts, it grows denser. As it grows denser, its gravity strengthens. And as gravity strengthens, the collapse accelerates. It's a feedback loop, elegant in its simplicity. Here's something that surprises many people. As the cloud collapses, it gets hotter, not cooler. This seems to defy our everyday experience. When we compress air in a bicycle pump, we feel it warm under our hands, but we might not connect this to the birth of stars. Yet, the principle is the same. When you compress a gas, you're forcing its atoms closer together, making them move faster and faster. Motion means higher temperature. In the collapsing nebula, gravitational energy converts into heat. This is one of the universe's fundamental principles, and it's absolutely crucial to star formation. Over perhaps 100,000 years, a protostar emerges. It's not yet a true star, this infant. It doesn't generate its own energy through fusion. Instead, it shines purely from the heat of its gravitational collapse. If you could somehow observe it, this protostar would glow with a deep red light, surrounded by a swirling disk of gas and dust. This disk is important. It's here that planets might one day form. But tonight we're focused on the star itself. The protostar continues to contract, and its core grows hotter. 10,000 degrees Kelvin, 100,000, a million. At these temperatures, atoms slam together with tremendous force. But still, fusion doesn't begin. The temperatures aren't yet high enough to overcome the electromagnetic repulsion between atomic nuclei. Protons, you see, all carry positive electrical charges, and like charges repel. To force them together requires extraordinary heat and pressure. And here we encounter one of the most beautiful moments in cosmic history. After perhaps another million years of contraction, the core temperature reaches approximately 10 million degrees Kelvin. The pressure is now about 250 billion times Earth's atmospheric pressure. And in this cosmic forge, hydrogen nuclei finally have enough energy to overcome their mutual repulsion. Two protons collide and fuse, beginning a chain reaction that will power the star for billions of years to come. The star ignites. Light is born. This moment, this transition from protostar to true star, is called reaching the main sequence. And it's marked by a profound balance. The inward pull of gravity is exactly matched by the outward pressure of the energy released by fusion. The star stops collapsing. It reaches equilibrium. It becomes stable. And in that stability, it can burn steadily for an almost incomprehensible span of time. Let's pause here and consider a common misconception, one that even many science communicators perpetuate. Stars don't burn. Not in the way a fire burns would, consuming fuel with oxygen and releasing heat. There's no oxygen in a star's core, no combustion in the chemical sense. What's happening is nuclear fusion, a fundamentally different process. Hydrogen nuclei are being forced together so violently that they fuse into helium-releasing energy. According to Einstein's famous equation, E equals mc squared. A tiny amount of mass converts into a tremendous amount of energy. This isn't burning, it's transmutation alchemy on a cosmic scale. The Orion Nebula that I mentioned earlier isn't just historical interest. Right now, at this very moment, it contains about 700 stars that have already formed, and perhaps 200 more in various stages of formation. When astronomers point their telescopes at this celestial nursery, they can see stars at every phase of birth. Some are still deeply embedded in their cocoons of gas and dust, visible only in infrared light. Others have blown away their surrounding material and shine brilliantly in visible light. It's like watching a time lapse of star formation, all happening simultaneously. And here's something that should fill you with wonder as you rest tonight. The process I've just described, this patient gathering of hydrogen into a star, has happened countless times across the history of the universe. The first stars formed just 100 million years after the Big Bang, condensing from pure hydrogen and helium in the ancient darkness. Later generations like our own sun formed from gas clouds enriched with heavier elements, elements forged in the hearts of earlier stars. Each generation building on the last, each star, a link in an unbroken chain stretching back to the beginning of time. The star that eventually became our sun formed about 4.6 billion years ago in a nebula not unlike Orion. We can know this because we can study meteorites' pristine remnants from the solar system's formation. Some of these meteorites contain tiny grains of material that predate the sun interstellar dust that survived the collapse and still carries the chemical signatures of earlier stars. When you hold a meteorite, you're touching material older than our world, older than our star. Think about the atoms in your own body for a moment. The oxygen you breathe, the carbon in your cells, the iron in your blood. None of these elements existed when the universe began. The Big Bang created only hydrogen, helium, and traces of lithium. Every other element, including those that make up your body, was forged in the core of a star or in the violent explosion of a supernova. You are quite literally made of stardust. The process we've explored tonight, the birth of stars from nebulae, is the same process that created the elements necessary for your existence. You are intimately connected to these cosmic cycles as you prepare to let sleep take you. Consider this star formation hasn't stopped. It continues tonight, tomorrow, and far into the future. In our own Milky Way galaxy, about 7 new stars are born every year. Across the observable universe, the number is staggering, perhaps 100 stars being born every second. The universe is not static, not finished. It's alive with creation, a vast garden constantly bringing forth new light. The journey from nebula to newborn star takes millions of years, an expanse of time difficult for our human minds to grasp. Yet, from the star's perspective, if stars could have perspectives, this is just the beginning. The main sequence, the stable phase we've reached, will last far, far longer. For a star like our Sun, 10 billion years of steady burning lies ahead. But what exactly happens in those cores where hydrogen becomes helium and light is born? How does fusion work, and why does it release such tremendous energy? The mechanism is beautiful, surprising, and worthy of our gentle attention. Deep within the core of a star, in a space no larger than Earth itself, something extraordinary happens every single second. 600 million tons of hydrogen vanish. They don't simply disappear into nothing. They transform into helium, and in that transformation, 4 million tons of matter convert purely into energy. This is the engine that powers our Sun, the furnace that has burned steadily for 4.5 billion years. And tonight, we're going to understand exactly how it works. If this gentle exploration of cosmic mysteries brings you peace, I invite you to subscribe and tap the like button. Your support allows me to continue creating these calming journeys through science, and I'm deeply grateful for it. Let's descend now into the heart of a star. Imagine you could journey to the Sun's center, traveling through 432,000 miles of stellar material. The conditions you'd encounter there are beyond anything we experience on Earth. The temperature is 15 million degrees, Kelvin, hot enough that matter exists only as plasma, a soup of naked atomic nuclei and free electrons. The pressure is 265 billion times Earth's atmospheric pressure. At this pressure, a volume of core material the size of a sugar cube would weigh more than a small car. In these extreme conditions, hydrogen nuclei, which are simply protons, move at incredible speeds. They collide constantly billions upon billions of times every second. And here, we encounter something beautiful and strange. Despite these countless collisions, fusion is actually a rare event. This might surprise you. With all that heat and pressure, all those high-speed impacts, why doesn't every collision result in fusion? The answer lies in one of nature's fundamental forces, electromagnetism. Each proton carries a positive electrical charge, and one of the iron laws of electromagnetism is that like charges repel. When two protons approach each other, they experience a powerful repulsive force. It's as if each proton is surrounded by an invisible shield pushing others away. To fuse two protons must get close enough for the strong nuclear force to take over a distance of about 1 femtometer, which is 1/millionth of 1/billionth of a meter. Getting that close requires enormous energy. Even at 15 million degrees, even with that crushing pressure, most proton collisions simply bounce off each other. They don't have quite enough energy to overcome the electromagnetic repulsion. Classical physics would say fusion is impossible under these conditions. The protons simply don't move fast enough. And yet, fusion happens. The sun shines. Every star in the night sky glows with fusion's light. How is this possible? The answer is one of the most beautiful revelations of quantum mechanics tunneling. In the quantum world, particles don't have precise positions or velocities. Instead, they exist as clouds of probability. A proton isn't really a tiny ball at a specific location. It's a wave function, a mathematical description of where it might be. And occasionally, remarkably, a proton can appear on the other side of the electromagnetic barrier without having enough energy to classically overcome it. It tunnels through ghosting, past the repulsive force that should keep it away. This tunneling is extremely rare for any individual proton. You might think this would make fusion too slow to power a star. But remember, there are an almost incomprehensible number of protons in a star's core. In just 1 gram of the sun's core material, there are approximately 600 billion protons. With numbers that vast, even rare events happen constantly. And so, fusion proceeds steadily, reliably at exactly the rate needed to balance gravity's inward pull. Let me walk you through what happens when 2 protons successfully fuse. This process is called the proton-proton chain, and it was worked out by Hans Bethe in 1938. Bethe was a German-born physicist who fled Nazi Germany and continued his work in the United States. His calculations explaining how stars shine earned him the Nobel Prize in Physics in 1967, almost 30 years after his discovery. Sometimes science requires patience, even in recognition. When two protons overcome their electromagnetic repulsion and get close enough, the strong nuclear force binds them together. But two protons alone can't form a stable nucleus. Something else must happen. In a process that involves the weak nuclear force, one of the protons transforms into a neutron, releasing a positron and a neutrino. The positron almost immediately encounters an electron, and they annihilate each other, converting their mass into energy in the form of gamma rays. The neutrino, nearly massless and barely interacting with matter, streams away at the speed of light. What remains is a nucleus containing one proton and one neutron. This is deuterium-heavy hydrogen. The deuterium nucleus then collides with another proton, fusing to create helium-3, which has two protons and one neutron. Finally, two helium-3 nuclei fuse together, creating helium-4, which has two protons and two neutrons and releasing two protons back into the mix. The net result, 4 hydrogen nuclei in one helium nucleus, out plus energy. Now, let's talk about that energy. This is where Einstein's most famous equation E equals mc squared becomes tangibly real. The helium nucleus produced by fusion weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has vanished. Where did it go? It converted into energy, and because c, the speed of light is such an enormous number, and because we square it in the equation, even a tiny amount of mass yields a staggering amount of energy. Let me give you a comparison that might help you grasp the scale. 1 gram of matter in the sun's core through fusion releases as much energy as burning 20 tons of coal, 20 tons from a single gram. This is why stars can shine for billions of years. The energy density of fusion is so high that even the slow, careful burning of the proton-proton chain can power a star across geological timescales. Here's something that might surprise you. The sun's core actually produces less energy per unit volume than your own body. This seems impossible. The sun is our model of a powerful energy source. But it's true. The core generates about 276 watts per cubic meter. A human body at rest produces about 100 watts per cubic meter. And when you're exercising, much more. The difference is scale. The sun's core is vastly larger than any human, and it sustains this energy production continuously for billions of years. You can think of the sun not as a roaring furnace, but as a steady, patient heater, producing warmth through sheer size and constancy rather than intensity. The energy released in the core doesn't immediately escape. This is crucial to understanding how stars work. The gamma rays produced by fusion are immediately absorbed by the dense plasma surrounding them. They transfer their energy to nearby particles, which then re-emit new photons. These new photons travel a short distance before being absorbed and re-emitted again. Each photon takes a random walk bouncing around inside the star, like a ball in an infinitely complex pinball machine. The distance between absorptions is called the mean free path. And in the sun's core, it's about 1 centimeter. 1 centimeter doesn't sound like much, but the photon must travel from the core to the surface, a distance of 700,000 kilometers. And it takes a random path, not a straight line. Calculations suggest that a single photon might take 100,000 to 200,000 years to make this journey. The light warming your face on a sunny day began its journey in the sun's core when the last ice age was ending, and woolly mammoths still walk the earth. But there's something else produced in the core that doesn't take this meandering path: neutrinos. Remember those nearly massless particles released in the first step of the proton-proton chain? Neutrinos barely interact with matter. They can pass through the entire sun as if it weren't there. From the moment they're created in the core, they stream outward at nearly the speed of light, reaching the surface in just 2.3 seconds. 8 minutes later, they pass through Earth through you utterly unnoticed. Billions of neutrinos from the sun pass through your body every second, night and day, and you never feel a thing. In the 1960s, physicist Raymond Davis Jr. built a detector deep underground in South Dakota to catch these solar neutrinos. His experiment used 100,000 gallons of cleaning fluid, and the neutrinos would occasionally interact with chlorine atoms in the fluid, converting them to radioactive argon. Davis could count these argon atoms and thus count neutrinos. The experiment was phenomenally difficult. He detected only about one neutrino interaction per day. But this was enough to prove that nuclear fusion really does power the sun. Davis shared the Nobel Prize for this work in 2002. Interestingly, Davis initially detected only about 1/3 as many neutrinos as theory predicted. This was called the solar neutrino problem, and it puzzled physicists for decades. The solution turned out to require modifying our understanding of neutrinos themselves. It wasn't the sun that needed explaining differently, but rather the fundamental physics of these ghost-like particles. They oscillate between different types as they travel, and Davis's detector could only catch one type. Modern detectors sensitive to all types measure exactly the number of neutrinos predicted by the theory of stellar fusion. Think about what this means. We have directly detected the products of fusion happening in the sun's core right now. Not light that took hundreds of thousands of years to escape, not indirect evidence, but particles created in the core and streaming to us in real time. We have, in a very real sense, seen into the heart of our star. The proton-proton chain is the dominant fusion process in stars about the size of the sun or smaller. But more massive stars with hotter cores use a different mechanism called the CNS cycle, or carbon-nitrogen-oxygen cycle. This process was also worked out by Hans Bethe and independently by Carl Friedrich von Weizsäcker. In the CNS cycle, carbon, nitrogen, and oxygen act as catalysts facilitating the fusion of hydrogen into helium without being consumed themselves. The end result is the same hydrogen to helium, but the process is more complex and operates at higher temperatures. The beauty of stellar fusion isn't just in its power, but in its steadiness. Once a star reaches the main sequence and fusion begins, the process self-regulates with elegant precision. If fusion produces too much energy, the star expands slightly, cooling the core and slowing fusion. If fusion produces too little energy, the star contracts slightly, heating the core and speeding fusion. This negative feedback loop, this thermostatic control, is why stars can burn so steadily for so long. The sun's output has varied by less than 1% over the past several billion years. This stability has been essential for life on Earth. As you rest here tonight, consider this. The fusion happening in stars is the reason the universe is not a lifeless void of hydrogen and helium. Every element heavier than helium was forged in stellar cores or in the violent deaths of massive stars. The oxygen you breathe was created inside a star 3 times the mass of the sun. The calcium in your bones came from a star at least 8 times the sun's mass. The iron in your blood was forged in a star that ended its life in a supernova explosion. And the gold in any jewelry you might wear was created in the collision of 2 neutron stars, remnants of massive stars crushed by gravity. Fusion is not just the power source of stars. It's the creator of complexity in the universe. And as we've seen tonight, it operates on principles that are both understandable and profoundly strange. It requires temperatures we can barely imagine, yet produces less energy per volume than your own body. It should be impossible according to classical physics, yet happens constantly through the quantum phenomenon of tunneling. It releases its light immediately to the cosmos in the form of neutrinos, yet locks its photons in a centuries-long random walk. The core of a star is not like any furnace we've built on Earth. It's a quantum engine operating at the intersection of gravity, electromagnetism, and nuclear forces. And its steady burn sustained over billions of years is what makes everything else possible. But the core is just the beginning of the star's structure. Between that fusion-powered heart and the surface, we see lie layers of material, each with its own character, its own role in the stellar symphony. A photon of light is born in the furnace of the sun's core. It carries energy from fusion, ready to fly free into space at 186,000 miles per second. But it doesn't. Instead, it begins a journey so strange, so labyrinthine, that by the time it finally emerges into space, humans may have risen and fallen as a civilization. This photon will travel less than an inch before it's absorbed, re-emitted, absorbed, again, scattered, redirected, transformed. It will take not 8 minutes to reach the surface, but 100,000 years. The star is not a simple sphere of gas. It's an architecture of layers, each one playing its part in transforming the violent energy of fusion into the gentle warmth that makes life possible. If these journeys through stellar science bring you comfort as you rest, please consider subscribing and leaving a like. It helps this channel reach others seeking peaceful understanding of our universe. Let's trace that photon's path outward from the core layer by layer and discover the hidden structure of a star. The sun, our closest star, will be our guide, but remember that what we learn here applies to countless stars across the cosmos. The journey begins in the core, that central region, extending to about 1/4 of the sun's radius. We have already explored the fusion happening here, the temperatures of 15 million degrees, the crushing pressures. But now, we need to understand how energy escapes. In the core, matter is so dense, so tightly packed that photons can barely move. The mean free path, the average distance a photon travels before interacting with matter, is roughly 1 centimeter. Imagine trying to walk through a crowd so dense that you can only move 1 centimeter before bumping into someone. Then imagine that every time you bump into someone, you're turned around and sent in a completely random direction. This is the photon's experience. The mathematics of this random walk are fascinating. When something takes random steps, the distance it travels isn't simply the number of steps multiplied by the step length. Because the steps are in random directions, they often cancel each other out. The actual distance traveled goes as the square root of the number of steps. To traverse the 700,000 kilometers from core to surface, a photon taking 1 centimeter steps needs to take about 10 to the power of 37 steps. That's 10 trillion steps. Even at the speed of light, this takes between 100,000 and 170,000 years, depending on which models you use. But as the photon diffuses outward, it enters a new zone, the radiative zone. This region extends from about 0.25 to 0.7 solar radii. Here, energy still moves primarily through radiation photons being absorbed and re-emitted. But the conditions are different from the core. The temperature has dropped to about 7 million degrees at the inner boundary and 2 million degrees at the outer edge. The density has decreased as well. Matter is still plasma, still ionized, but less tightly packed. In the radiative zone, energy transport is orderly, predictable. Heat flows from hotter regions to cooler regions through this diffusion of radiation. It's a slow process, but it's steady. Think of it like this. Imagine you have a hot stone in the center of a pile of sand. The heat doesn't instantly reach the surface. It gradually diffuses outward grain by grain as each particle transfers energy to its neighbors. The radiative zone works similarly, except the particles are ions and electrons, and the energy carriers are photons. What's remarkable about the radiative zone is its stability. There's no large-scale motion of material here, no convection, no mixing. The same atoms that were in the radiative zone when the sun formed 6 billion years ago are still there today in essentially the same positions. This zone is a fossil preserving the original composition of the solar nebula. If we could somehow sample material from the radiative zone, we'd be analyzing matter that hasn't been processed through the core matter that still reflects the primordial mix of elements from the sun's birth cloud. But as we move outward, we encounter a profound transition. At about zero point 0.7 solar radii, something changes. The temperature has dropped to about 2 million degrees. At this temperature, hydrogen and helium begin to hold on to some of their electrons. They're not fully neutral atoms yet, but they're not fully ionized plasma either. And this partial ionization changes everything. These partially ionized atoms are very good at absorbing radiation. The material becomes opaque. Energy can no longer efficiently move through radiation alone. The photon's random walk becomes too slow. When a fluid is heated from below and can't transport heat fast enough through radiation or conduction, something dramatic happens. It begins to convect. Hot material, being less dense, rises. Cool material, being more dense, sinks. This sets up enormous circulation patterns, and we've entered the convective zone. In the sun's convective zone, which extends from 5.7 solar radii all the way to the visible surface, plasma moves in vast cells like water boiling in a pot, but on an unimaginable scale. A single convection cell might be as large as Earth itself. Hot plasma rises from the bottom of the zone, cools as it approaches the surface, then sinks back down. The process is far more efficient at transporting energy than radiation. What took 100,000 years to travel through the radiative zone takes only about a week to traverse the convective zone. If you've ever watched water begin to boil, you've seen convection in action. Small bubbles form at the bottom, where the heat source is hottest. They rise, expand as they enter lower pressure, and eventually burst at the surface. The sun's convection is similar, but far more complex. The plasma doesn't form discrete bubbles. Instead, it organizes into elaborate patterns, hexagonal cells visible on the sun's surface as granulation. Each granule a cell of rising hot plasma, surrounded by cooler sinking plasma, is about 1,000 kilometers across. The entire visible surface of the sun is covered with these granules constantly forming, evolving, and dissipating. Each one lasts only about 8 to 20 minutes. When astronomers first observed solar granulation in the mid-1800s, they didn't immediately understand what they were seeing. Some thought the sun had a solid surface with holes through which internal fires shone. Others proposed that the sun was a cool, inhabited planet, surrounded by a luminous atmosphere. It wasn't until the early 20th century, with the development of theories about stellar structure and the understanding of convection, that the true nature of granulation became clear. Now, we reach the photosphere, the visible surface of the sun. This isn't a solid surface, of course. There's no sharp boundary where gas ends and space begins. The photosphere is simply the layer from which photons can finally escape to space without being immediately absorbed. It's about 500 kilometers thick-thin compared to the sun's radius of 700,000 kilometers. The temperature here is about 5,500 degrees Celsius cool compared to the interior, but still hot enough to vaporize any material we know. The photosphere is where our photon, after its 100,000-year journey from the core, finally becomes visible light that can cross space freely. And it's worth pausing to appreciate how profoundly the photon has been transformed. It began as a high-energy gamma ray, the product of fusion. Through countless absorptions and re-emissions, each one sapping a bit of energy, it has been downshifted in frequency. By the time it emerges from the photosphere, it's likely a visible light photon, perhaps yellow or green. The star has taken the violent output of nuclear fusion and gentled it, transformed it into the light that warms planets, and on at least one world enables life to flourish. But the star's structure doesn't end at the photosphere. Above this visible surface lies the chromosphere, a layer about 2,000 kilometers thick. The name comes from the Greek for color sphere, because it appears as a thin reddish arc during solar eclipses just before and after totality. This red color comes from hydrogen alpha emission light, produced when electrons and hydrogen atoms drop from the third to the second energy level. Here's something that puzzled astronomers for over a century. The chromosphere is hotter than the photosphere below it. The temperature rises from 5,500 degrees at the top of the photosphere to about 20,000 degrees in the chromosphere. This seems to violate the second law of thermodynamics. Heat should flow from hot to cold, not the reverse. How can the outer layers be hotter than the layers below? The answer involves the transfer of energy not through heat, but through magnetic fields and waves. The sun's convective zone acts like a giant dynamo, generating powerful magnetic fields. These fields extend up through the photosphere into the chromosphere and beyond. Magnetic waves propagating along these field lines carry energy outward. When these waves dissipate, they deposit their energy as heat. It's not heat flowing uphill, but rather a separate form of magnetic energy being converted to heat in the upper atmosphere. The full details are still being worked out, but the general mechanism is understood. Beyond the chromosphere lies the corona, the sun's outer atmosphere. This region, visible to the naked eye during total solar eclipses as a pearly white halo around the darkened sun, is one of the most spectacular and mysterious parts of our star. The corona is tenuous, far less dense than the photosphere or chromosphere, and yet it's astoundingly hot. Temperatures in the corona reach 1 to 3 million degrees Celsius, hundreds of times hotter than the visible surface. When the corona was first studied spectroscopically in the late 1800s, astronomers found emission lines that didn't match any known element. Some scientists proposed the existence of a new element, coronium, found only in the sun's outer atmosphere. It wasn't until 1939 that Bengt Edlund, a Swedish physicist, solved the mystery. The mysterious lines weren't from a new element. They came from ordinary iron, but iron that had been stripped of many electrons. To ionize iron to this degree requires temperatures in the millions of degrees. This was the first solid evidence that the corona is extraordinarily hot. The coronal heating problem, as it's called, remains one of the great puzzles in solar physics. The general consensus is that magnetic fields are again responsible. The sun's magnetic field lines extend into the corona and can become twisted and stressed as the solar surface rotates and convects. When these twisted field lines snap and reconnect, they release energy. Additionally, magnetic waves propagating from below may dissipate in the corona. But the exact balance of mechanisms that detail physics of how the corona reaches such high temperatures is still an area of active research. From the corona, material can escape the sun's gravity entirely, flowing outward as the solar wind. This wind of charged particles streams through the solar system at speeds of 300 to 800 kilometers per second, carrying the sun's magnetic field with it. It shapes the magnetic environments of all the planets, causes auroras on Earth, and defines the boundary between the solar system and interstellar space. Let's step back and appreciate the architecture we've explored. From the core outward, the fusion furnace generating energy. The radiative zone slowly diffusing that energy outward through countless photon interactions. The convective zone carrying energy efficiently through bulk motion of plasma. The photosphere, the visible surface from which light finally escapes. The chromosphere glowing red with hydrogen emission. The corona mysteriously heated to millions of degrees, and beyond the solar wind carrying the sun's influence across billions of miles. Each layer has its own temperature, its own density, its own way of transporting energy, and yet they all work together in a harmony governed by the laws of physics. The structure we see, the layers that exist, are not arbitrary. They emerge naturally from the interplay of gravity energy generation and the properties of matter at different temperatures and pressures. Other stars have similar structures, but the details vary. More massive stars might have convective cores and radiative outer layers, the opposite of the sun. Lower mass stars might be convective throughout. The thickness of each zone, the temperatures and densities all depend on the star's mass and composition. But the principles remain the same. Energy generated in the core must make its way to the surface, and the method by which it does so determines the star's structure. As you lie here, perhaps beginning to drift towards sleep, consider this. The light that warms your world, began its journey before modern humans existed. The photons that will illuminate Earth tomorrow started their outward trek when Neanderthals still lived in Europe, and the photons being born in the sun's core right now won't reach us until our distant descendants walk the planet, if they exist at all. The star connects deep time to the present moment, links the ancient past with the far future, all in the gentle glow of its light. This layered structure, this patient transformation of fusion's violence into warmth, is not just the sun's story. It's the story of every main sequence star in the universe. And understanding these layers, understanding how energy flows from core to space, brings us to one of the most fundamental questions in astrophysics. What keeps a star from collapsing under its own gravity, or from exploding outward? What maintains that perfect balance? Imagine standing on the edge of a cliff perfectly balanced. One step forward and you fall. One step back and you're safe. Now imagine maintaining that exact balance not for a moment, but for 10 billion years. This is what a star does every single second of its existence. It balances on a knife's edge between catastrophic collapse and explosive expansion, held in perfect equilibrium by forces so precisely matched that the difference between them is essentially zero. This balance, called hydrostatic equilibrium, is perhaps the most elegant example of nature's ability to find and maintain stability in what seems like an impossible situation. If you're finding peace in understanding these cosmic principles, I'd be honored if you'd subscribe and leave a like. These small gestures help others discover this gentle approach to science. Let's understand this balance by first considering what would happen if it failed. Imagine for a moment that fusion in the sun's core suddenly stopped. No more energy generation, no more outward pressure from the heat of fusion. What would happen? Gravity unopposed would begin to compress the sun. And here's where it gets interesting. As the sun compressed gravitational potential, energy would convert to heat, just as it did during the initial collapse that formed the star. The core would actually get hotter. If it got hot enough, fusion would reignite. The star would find its balance again. Now, imagine the opposite scenario. Suppose fusion suddenly accelerated, producing far more energy than normal. The core would heat up dramatically. The increased temperature would create increased pressure, and the star would begin to expand. As it expanded, the core would cool and become less dense. Fusion rates depend strongly on temperature and density, so as the core cooled and thinned, fusion would slow down. The star would contract back toward equilibrium. This is hydrostatic equilibrium's beautiful secret. It's self-correcting. Stars are naturally stable because any deviation from balance triggers a response that brings them back. It's a negative feedback loop, like a thermostat, maintaining your home's temperature. Too hot and the air conditioning turns on. Too cold and the heating engages. In a star, too much fusion causes expansion and cooling. Too little fusion causes contraction and heating. The mathematical expression of hydrostatic equilibrium is remarkably simple. At any point inside a star, the inward force of gravity must exactly equal the outward force of pressure. We can write this as a differential equation. The change in pressure with radius equals negative. The density times the gravitational acceleration. Simple to write, but profound in its implications. This single equation, combined with a few others describing energy transport and energy generation, is sufficient to calculate the entire structure of a star. Given a star's mass and composition, we can predict its radius, luminosity, core temperature, and lifetime with impressive accuracy. The first person to work out the mathematics of stellar equilibrium was Arthur Eddington, the British astronomer, who also confirmed Einstein's theory of general relativity. In his 1926 book, The Internal Constitution of the Stars, Eddington laid the foundation for modern stellar astrophysics. He showed that stars must have enormously hot cores to generate the pressure needed to support themselves against gravity. Many scientists at the time found this conclusion hard to accept. Temperatures of millions of degrees seemed impossibly high. But Eddington was right, and his work opened the door to understanding stellar structure. Here's a way to visualize the balance. Imagine the star divided into thin shells like an onion. Each shell has weight the gravitational force pulling it inward. The shell below must provide enough pressure to support this weight. If it doesn't, the shell collapses. If it provides too much pressure, the shell is pushed outward. Only when the pressure is exactly right does the shell remain stationary. Now, extend this to every shell in the star, from the outermost layers down to the core. Each shell must provide precisely the pressure needed to support all the shells above it. The pressure in a star comes from two sources: thermal pressure and radiation pressure. Thermal pressure is what we are familiar with from everyday gases. It's the pressure created by atoms and ions bouncing around at high speeds. The faster they move, meaning the higher the temperature, the more pressure they create. Radiation pressure comes from photons. Light carries momentum, and when photons bounce off particles, they exert a force. In the sun, thermal pressure dominates, but in very massive stars with extremely hot cores, radiation pressure can become significant or even dominant. Let's look at a real example of this balance in action. In October 2019, the star Betelgeuse, a red supergiant in the constellation Orion, began to dim dramatically. By February 2020, it had lost more than 60% of its brightness. Astronomers around the world turned their telescopes toward this familiar star, and speculation ran wild. Was Betelgeuse about to explode as a supernova? Was this the beginning of the end for one of the most recognizable stars in the night sky? What we were witnessing was actually a disruption of Betelgeuse's equilibrium. Red supergiants like Betelgeuse are already highly unstable. They're so large and their outer layers are so cool that they pulsate, expanding and contracting over periods of months or years. During this particular event, a large mass of material was ejected from the star's surface, forming a dust cloud that blocked much of its light. The star had lost equilibrium, temporarily ejecting material before settling back into a new, slightly different balance. Betelgeuse eventually brightened again, reaching normal levels by April 2020. But this event taught us something important. Even the equilibrium of a massive star is dynamic, not static. The star constantly adjusts, responding to changes in fusion rate, to the loss of mass from stellar winds, to the complex interplay of forces in its interior. Betelgeuse's dimming was a reminder that stellar equilibrium, while robust, is also flexible. Stars are not rigid structures. They are fluid, responsive, alive in a way that few astronomical objects are. Another dramatic example of equilibrium under stress comes from binary star systems. When two stars orbit each other closely, their mutual gravity can distort their shapes. Instead of being spherical, they become elongated, egg-shaped. Each star is now being pulled, not just by its own gravity, but by its companion's gravity as well. Yet, remarkably, hydrostatic equilibrium still holds. The pressure at any point in each star still balances the gravitational force at that point. The equilibrium adapts to the new geometry. In some binary systems, one star can pull material from its companion. If the companion is a red giant with an extended atmosphere, the denser partner's gravity can strip away the outer layers. This material spirals inward, forming an accretion disk around the star that's gaining mass. The temperature and pressure in this accretion disk reach extremes sometimes hot enough to emit X-rays. And still, each small element of the system remains in its own local equilibrium, pressure balancing gravity, even in this chaotic environment. Let's consider what determines the exact point of equilibrium for any given star. Why does a star of a particular mass settle at a particular radius and luminosity? The answer lies in the mass-luminosity relationship, another of Eddington's discoveries. More massive stars are not just brighter, they're dramatically brighter. A star twice as massive as the Sun is not twice as bright, but about 10 to 16 times as bright. A star 10 times as massive as the Sun is thousands of times brighter. This happens because more massive stars need higher core temperatures to generate enough pressure to support their greater weight. Higher core temperatures mean faster fusion rates, and faster fusion means greater luminosity. The relationship is steep, approximately luminosity proportional to mass to the 3.5 power. This has profound consequences for stellar lifetimes, as we'll explore later. But for now, what matters is that the star's mass determines its equilibrium state. Give me a star's mass, and I can tell you its radius, its luminosity, its core temperature, everything about its structure. There's a limit to how massive a star can be, and still maintain hydrostatic equilibrium. At masses above about 150 to 200 solar masses, radiation pressure becomes so intense that it overcomes gravity and blows the star apart. These hypothetical stars would be unstable from birth. They might form briefly, but they'd quickly lose mass through powerful stellar winds until they drop below the critical threshold. This is called the Eddington limit, and it sets an upper bound on stellar mass. At the other extreme, there's a lower limit too. Below about 0.08 solar masses, the core never gets hot enough to sustain hydrogen fusion. These objects, called brown dwarfs, are failed stars. They glow dimly from the heat of their gravitational contraction and from the fusion of deuterium, a rare isotope of hydrogen that requires lower temperatures. But they never achieve true hydrostatic equilibrium, powered by ordinary hydrogen fusion. They're not quite stars, not quite planets, but something in between. Let's talk about a common misconception. Many people imagine that the pressure supporting a star comes from the fusion reactions themselves, like the pressure from a continuous explosion. But this isn't correct. Fusion generates heat, and that heat creates pressure through the thermal motion of particles. But fusion doesn't directly push outward. If fusion stopped right now in the sun, the pressure wouldn't drop immediately. The heat would still be there, still supporting the star, at least for a while. The real crisis would come gradually, as the star radiated away its stored thermal energy and began to cool and contract. In fact, we can calculate how long the sun could support itself against gravity using only its stored thermal energy with no fusion at all. This is called the Kelvin-Helmholtz timescale, named after Lord Kelvin and Hermann von Helmholtz, who calculated it in the 19th century before nuclear fusion was understood. For the sun, this timescale is about 30 million years. That's how long the sun could shine at its current brightness, using only gravitational contraction for energy. Kelvin and Helmholtz thought this was the actual age of the sun, which conflicted with geological evidence suggesting Earth was much older. The resolution came with the discovery of nuclear fusion, which provides a much longer-lasting energy source. The equilibrium of a star is also affected by rotation. Our sun rotates once every 25 days at its equator and every 35 days near its poles. This differential rotation is possible because the sun is not solid. Different parts can rotate at different speeds. Rotation creates a centrifugal effect that slightly reduces the effect of gravity, particularly at the equator. The sun bulges slightly at the equator and is flattened at the poles as a result. The difference is small, only about 10 parts per million, but in rapidly rotating stars, the effect can be dramatic. Some stars rotate so fast that their equatorial radius is significantly larger than their polar radius. They're noticeably egg-shaped, and their equilibrium must account for this distortion. Magnetic fields add another layer of complexity. The sun's magnetic field, generated by the motion of charged plasma in the convective zone, stores energy. In principle, this magnetic energy could contribute to supporting the star. In practice, the contribution is negligible for the sun. But in magnetic stars, particularly neutron stars, with magnetic fields, trillions of times stronger than Earth's magnetic pressure become significant. These exotic objects maintain equilibrium through a combination of degeneracy pressure, which we won't delve into tonight, and magnetic pressure. As you rest here, breathing slowly, your own body maintains countless equilibria. Your blood pressure regulated by your heart and blood vessels. Your body temperature regulated by metabolism and heat loss. the chemical balance of ions in your cells regulated by molecular pumps. In a sense, you and the stars are doing the same thing, finding and maintaining balance in systems that could easily spiral out of control. The scales are different, the forces are different, but the principle is the same. Stability emerges from the careful balancing of opposing tendencies. The star's hydrostatic equilibrium is not just a curious fact. It's the reason stars exist as distinct long-lived objects, rather than as expanding clouds of gas or collapsed points. It's why stars shine steadily for billions of years rather than flickering chaotically. It's why we can predict stellar evolution with such precision. The balance between gravity and pressure is in many ways the foundation of everything else we know about stars. But this equilibrium, stable as it is, tells us something else through its very existence. The fact that pressure can balance gravity means that the star must be hot inside. And the fact that the star continuously radiates energy into space means that it must be replacing that energy somehow. The balance reveals not just stability, but the necessity of an internal energy source. And that energy source, as we've seen, is fusion. The equilibrium doesn't just describe the star's structure. It explains why stars must be fusion-powered furnaces. Yet, when we look up at the night sky, we see stars of many different colors, different brightnesses, different characteristics. If all stars are balanced between gravity and pressure, why don't they all look the same? What makes one star red and another blue, one star bright and another faint? When you look up at the night sky, you might think all stars appear, white tiny points of light scattered across the darkness. But look more carefully, perhaps, on a clear winter night when the air is steady and cold. Some stars shine with a distinctly reddish tint. Others glow blue-white, almost icy in their brilliance. These colors aren't accidents of observation or tricks of the atmosphere. They're messages written in light, carrying information about the star's temperature, its age, its composition, even its fate. Every star is speaking to us through its color if we know how to listen. And the story begins with heat. If these quiet revelations about starlight help you find rest, please take a moment to subscribe and like this video. Your support allows these peaceful explorations to continue. The connection between color and temperature is something we can observe in everyday life. Heat a metal poker in a fire, and it first glows dull red. As it gets hotter, it brightens to orange, then yellow, then white, and if you could heat it hot enough without it melting, it would glow blue-white. This sequence from red through orange and yellow to white and blue is a temperature scale. Red means cooler, blue means hotter. Stars follow the exact same principle. The coolest stars with surface temperatures around 2,500 to 3,500 degrees. Kelvin glow deep red. These are the red dwarfs and red giant stars that dominate the galaxy by number, but are often invisible to the naked eye because they're so dim. At 5,500 degrees Kelvin, we find yellow stars like our sun, though the sun's light is actually white when viewed from space. Earth's atmosphere scatters the blue light, making the sun appear more yellow to us on the surface. The hottest stars with surface temperatures of 30,000 to 50,000 degrees. Kelvin burn with an intense blue-white light. These are rare, massive stars that live fast and die young. The physics behind this color-temperature relationship is called blackbody radiation, and it was worked out in the late 1800s and early 1900s by physicists including Gustav Kirchhoff, Max Planck, and Wilhelm Wien. A blackbody is an idealized object that absorbs all radiation falling on it and emits radiation based solely on its temperature. Stars approximate blackbodies quite well. When you heat an object, its atoms vibrate more vigorously, and these vibrations produce electromagnetic radiation. The hotter the object, the more energetic the vibrations, and the shorter the wavelength of the peak radiation. Wien's displacement law, formulated in 1893, gives us the precise relationship. The wavelength at which a blackbody emits most strongly is inversely proportional to its temperature. Multiply the peak wavelength in nanometers by the temperature in Kelvin, and you always get approximately 2.9 million. This simple relationship allows astronomers to determine a star's surface temperature just by analyzing its spectrum, the rainbow of colors it emits. But color tells us more than just temperature. It also reveals composition. In the early 1900s, astronomers began systematically studying stellar spectra, passing starlight through prisms to spread it into its component wavelengths. They noticed dark lines interrupting the rainbow absorption lines, where certain wavelengths were missing. Different stars showed different patterns of lines. Initially, stars were classified alphabetically by these patterns A, B, C, and so on, with A stars showing the strongest hydrogen lines. Then came Cecilia Payne, a young British astronomer working at Harvard College Observatory. In 1925, she completed her doctoral thesis, which would later be called the most brilliant PhD thesis ever written in astronomy. Payne analyzed the spectral lines of stars and, using the newly developed quantum theory, calculated the relative abundances of different elements. Her conclusion was shocking. Stars are made primarily of hydrogen and helium, with all other elements present in only trace amounts. This contradicted the accepted wisdom of the time, which held that stars had roughly the same composition as Earth, with heavy elements predominating. Payne's advisor, Henry Norris Russell, initially discouraged her from publishing this conclusion, saying it was impossible. 4 years later, Russell himself came to the same conclusion and is often incorrectly credited with the discovery. But history has righted this wrong. Today, Cecilia Payne-Gaposchkin, as she later became, is recognized as the astronomer who discovered what stars are made of. Her work revealed something profound. The spectral classification that astronomers had developed, those letters A, B, C, and so on, weren't really measuring composition. They were measuring temperature. The hydrogen lines aren't strongest in A stars because A stars have more hydrogen. They're strongest because A stars have the right temperature, about 10,000 Kelvin for hydrogen, to be in the precise state of ionization that produces those particular spectral lines. Once this was understood, the classification was reordered by temperature rather than alphabet O, B, A, F, G, K, M from hottest to coolest. Generations of astronomy students have memorized this sequence with the mnemonic, "Oh, be a fine girl, kiss me," though many modern variants exist. Let's look at two specific stars to make this concrete. Rigel, the bright blue-white star in Orion's foot, has a surface temperature of about 12,000 Kelvin. It's a B-type star, young and massive. The light from Rigel peaks in the ultraviolet, though it emits plenty of visible light as well. If you could somehow stand on a planet orbiting Rigel, the sunlight would be tinged blue, and you'd need serious protection from the intense ultraviolet radiation. The star would flood the planet with energy about 120,000 times the luminosity of our sun, packed into a star only about 80 times larger. Contrast this with Betelgeuse, the red supergiant marking Orion's shoulder. Betelgeuse has a surface temperature of only about 3,500 Kelvin, less than a third that of Rigel. Its light peaks in the infrared. Most of its radiation is heat rather than visible light. If you could stand on a planet orbiting Betelgeuse at a distance that received the same amount of total energy as Earth receives from the sun, the sky would glow deep red, almost crimson. The star would appear enormous, an angry red eye dominating the heavens. Here's a common misconception that I want to address. When we say a red star is cool, we're speaking relatively. Betelgeuse at 3,500 Kelvin is cooler than the sun at 5,500 Kelvin, which is cooler than Rigel at 12,000 Kelvin. But 3,500 Kelvin is still 3,200 degrees Celsius, hot enough to vaporize any substance we know instantly. There's no cool star in absolute terms. The coolest stars are still furnaces that would incinerate anything nearby. When astronomers talk about cool stars, we mean cool for a star, not cool in any everyday sense. The color of a star also tells us something about its age and stage of evolution, though the relationship is subtle. Main sequence stars, those actively fusing hydrogen in their cores, like the Sun, follow a clear pattern. More massive main sequence stars are blue and hot. Less massive main sequence stars are red and cool. But as stars age and leave the main sequence, the relationship changes. A star like the Sun will eventually become a red giant, expanding and cooling even as its core contracts and heats. Later, still, it will become a white dwarf, extremely hot, but so small that its total luminosity is low. When astronomers plot stars on a graph with temperature on one axis and luminosity on the other, the result is called a Hertzsprung-Russell diagram, named after Einar Hertzsprung and Henry Norris Russell, who independently developed it in the early 1900s. This diagram is one of the most important tools in astronomy. Most stars fall along a diagonal band called the main sequence, running from hot and bright at the upper left to cool and dim at the lower right. But there are also distinct populations of red giants, supergiants, and white dwarfs. The position of a star on this diagram tells its life story. The color of starlight changes as it travels through space, and this effect has revolutionized our understanding of the universe. When a star moves away from us, its light is redshifted, meaning all wavelengths are stretched to become slightly longer, slightly redder. When a star moves toward us, its light is blue shifted, compressed to shorter wavelengths. This is the Doppler effect, familiar from the changing pitch of a passing siren. By measuring the precise shift in a star's spectral lines, astronomers can calculate how fast it's moving toward or away from us. In 1929, Edwin Hubble used this technique to make one of the most important discoveries in the history of science. He measured the redshifts of distant galaxies and found that nearly all of them were moving away from us. More distant galaxies were receding faster. The universe itself was expanding. This observation, built on careful measurements of starlight colors, led directly to the Big Bang theory and revolutionized cosmology. Even more remarkably, astronomers have learned to detect planets around distant stars by watching for tiny periodic shifts in the star's color. As a planet orbits, its gravity tugs on the star, causing the star to wobble slightly. When the star moves toward us in its wobble, its light is slightly blue shifted. When it moves away, slightly red shifted. These shifts are incredibly small, sometimes less than 1 part per million, but modern instruments can measure them, and this technique, called radial velocity or Doppler spectroscopy, has discovered hundreds of exoplanets. The study of stellar colors and spectra has also revealed the existence of spectroscopic binary stars, pairs of stars so close together that we can't see them as separate points of light, even with our best telescopes. But we can see the spectral lines split into 2 sets, one from each star, and watch these line sets shift back and forth as the stars orbit each other. Some binary systems are discovered only through this effect, invisible to direct imaging, but revealed through patient analysis of starlight. Let's consider the star Sirius, the brightest star in Earth's night sky. To the eye, Sirius appears brilliant white, almost dazzling. Its spectral type is A1, meaning it's one of the hotter main sequence stars, at about 900 Kelvin. Sirius is only 8.6 light-years away, relatively close in cosmic terms. But Sirius has a companion, Sirius B, a white dwarf that orbits the bright star every 50 years. Sirius B was discovered in 1862 by Alvin Graham Clark, who noticed a faint point of light near Sirius while testing a new telescope. This white dwarf is far hotter than Sirius A, with a surface temperature of about 25,000 Kelvin. But it's so small, only about the size of Earth, that its total luminosity is less than 3% that of its companion. The existence of white dwarfs posed a major puzzle when they were first discovered. How could a star be simultaneously very hot and very dim? The answer required new physics. In the 1920s, Ralph Fowler and later Subrahmanyan Chandrasekhar showed that white dwarfs are supported not by thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect. The electrons in a white dwarf are packed so tightly that Quantum mechanics forbids them from being compressed further. This pressure can support the star, even when it's no longer generating energy through fusion. Color measurements have even allowed astronomers to determine the ages of star clusters. Stars in a cluster all formed at roughly the same time from the same cloud of gas. The most massive stars burn through their fuel quickly and leave the main sequence first becoming red giants or exploding as supernovae. By identifying which stars in a cluster have left the main sequence and which remain, astronomers can estimate the cluster's age. This technique, called main sequence turn-off dating, has shown that some globular clusters orbiting our galaxy are over 13 billion years old, almost as old as the universe itself. Think about how extraordinary this is. By analyzing light, by carefully measuring colors and wavelengths, astronomers can determine temperature composition, motion age mass, and evolutionary state. The light carries all this information encoded in wavelengths and intensities. We're reading the star's vital signs from trillions of miles away, diagnosing their conditions without ever visiting them. It's like a doctor determining your health by examining light reflected from your body, except the patient is a ball of plasma 1,000,000 times larger than Earth and impossibly distant. As you prepare for sleep, you might notice the subtle colors in your environment. The warm yellow of a bedside lamp, perhaps. The cool blue glow of moonlight through a window. These are the same phenomena at work in stars, the same physics of black-body radiation, just at vastly different scales and temperatures. The universe speaks one language, and that language is light. The colors we've explored, the temperatures they reveal, are not static. Stars change over time, evolving through different stages, living out lives that span billions or millions of years, depending on their mass. And it's to these timescales, these vast expanses of stellar existence, that our attention turns next. There's a star in our cosmic neighborhood, barely visible even with a telescope, that will outlive not just you and me, not just our civilization, not just our species, but the current age of the universe itself. Proxima Centauri, a small red dwarf just 4 light-years away, has enough fuel to burn for 4 trillion years. The universe is only 13.8 billion years old. Proxima Centauri could shine for nearly 300 times the current age of everything. And yet there are stars that lived their entire lives, were born and died, in less time than humans have walked upright on Earth. The paradox of stellar lifetimes is this: the bigger the star, the shorter it lives. And the difference isn't subtle, it's a factor of millions. If these meditations on cosmic time help you find perspective and peace, I'd be grateful if you'd subscribe and like this video. It truly helps this channel grow. Let's begin with a question that puzzled astronomers for decades. Why do massive stars with so much more fuel burn out so much faster? It seems backward. Imagine 2 cars, one with a small fuel tank and one with a large one. You'd expect the car with more fuel to run longer. But stars don't work like cars. The relationship between mass and lifetime is inverse, and it's steep. A star with 10 times the sun's mass has about 10 times as much fuel, but it burns through that fuel not 10 times faster, but thousands of times faster. It will live only about 20 million years compared to the sun's 10 billion. The reason lies in that mass-luminosity relationship we touched on earlier. More massive stars must generate enormously more energy to support themselves against their own gravity. A star 10 times the sun's mass shines about 10,000 times brighter. It's burning fuel at an extraordinary rate. And because luminosity increases faster than mass, the lifetime decreases dramatically. The mathematical relationship is roughly this: lifetime is inversely proportional to mass raised to the 2.5 power. Double a star's mass, and its lifetime drops by more than a factor of 5. Let's make this concrete by looking at specific examples. Our Sun, a G-type star with a mass of 1 solar mass by definition, has a main sequence lifetime of about 10 billion years. It's currently 4.6 billion years old, so it's roughly halfway through its hydrogen-burning phase. When we look at smaller stars, the lifetimes extend dramatically. A star with half the Sun's mass, an M-type red dwarf, will live for about 60 billion years. A star with a quarter of the Sun's mass could persist for 200 billion years or more. Now, consider Proxima Centauri specifically. With a mass of just 0.12 solar masses, about 12% of the Sun's mass, this tiny star burns its fuel so slowly, so carefully, that it could continue fusing hydrogen for approximately 4 trillion years. To put that in perspective, when Proxima Centauri finally exhausts its fuel and fades the cosmic microwave background radiation, the afterglow of the Big Bang will have cooled to near absolute zero. The universe will be cold, dark, and nearly empty. Galaxies will have dispersed into isolated stars drifting through void. And Proxima Centauri will have been there the entire time, quietly burning. At the other extreme, consider massive stars. Eta Carinae, one of the most massive stars we know, with perhaps 100 to 150 solar masses, is extraordinarily luminous, about 5 million times brighter than the Sun. It's consuming fuel at such a prodigious rate that its entire main sequence lifetime might be only 3 million years. 3 million years sounds like a long time to us, but geologically, it's a blink. When Eta Carinae formed, there were no humans, no primates, not even the dinosaurs. But there were mammals. The star has lived its entire life within the age of modern mammalian evolution. The most massive stars we've observed approaching 200 solar masses might live as briefly as 2 million years. These giants are so rare and so short-lived that at any given moment, there are very few of them in the entire galaxy. We're lucky to observe any at all, and when they die spectacularly in supernova explosions that briefly outshine entire galaxies. Here's something that really illuminates the scale we're discussing. Imagine compressing all of Earth's history, 4.5 billion years, into a single calendar year. January 1st, the Earth forms. Life appears in February. Oxygen accumulates in the atmosphere by late spring. Complex multicellular life doesn't evolve until November. Dinosaurs appear on December 13th and go extinct on December 26th. Humans appear on December 31st at about 11:30 p.m. All of recorded human history occupies the last few seconds before midnight. On this scale, a massive star's entire life, 2 to 3 million years, would be less than 6 hours. The star would be born live and die in a single morning of geological time. The red dwarfs, those patient dim stars, live so long that none have died yet. Not a single red dwarf that formed in the early universe has run out of fuel. They're all still burning. The universe simply hasn't existed long enough for even the oldest red dwarfs to complete their lives. This means we've never actually observed what happens when a red dwarf dies. We have theoretical models, calculations suggesting they'll quietly fade to white dwarfs, but we can't verify this empirically. We'll have to wait trillions of years for confirmation. This difference in lifetimes has profound implications for the search for life in the universe. Red dwarfs are by far the most common type of star making, up about 75% of all stars in the galaxy. Their longevity means that any planets orbiting them have enormous amounts of time for life to evolve. If life requires billions of years to become complex red dwarf systems, have those billions of years many times over. On the other hand, red dwarfs are prone to violent flares, especially when they're young, which might sterilize nearby planets. The question of whether red dwarf systems are good places for life remains open. Let's talk about why understanding stellar lifetimes matters beyond academic curiosity. When we look at distant galaxies, we're looking back in time. The light from a galaxy a billion light years away left that galaxy a billion years ago. We're seeing it as it was in the past. By studying which types of stars exist in galaxies at different distances, different cosmic times, astronomers can reconstruct the history of star formation in the universe. We know that star formation peaked about 10 billion years ago and has been declining since. We know this partly by observing the populations of stars at different epochs. The lifetime of stars also affects the chemical evolution of galaxies. Massive stars live fast, die young, and when they explode as supernovae, they enrich the interstellar medium with heavy elements. These elements are incorporated into the next generation of stars. Red dwarfs living so long lock up their material for eons. They don't contribute to chemical enrichment on human timescales or even on galactic timescales in the current universe. The pace at which a galaxy's chemical composition changes depends critically on the balance between massive short-lived stars and small, long-lived ones. There's a beautiful irony here. The stars we see most easily with our eyes, the brilliant blue and white stars like Rigel Spica and Vega, are the rarest and most ephemeral. They're cosmically young and they'll be gone relatively soon. The stars that will dominate the universe's future, the red dwarfs that will still be shining when everything else has faded, are mostly invisible to us. We can barely see them without telescopes. The universe's present is spectacular and bright, full of variety. But its distant future belongs to the small, the dim, and the patient. Consider what this means for cosmic history. The universe is currently in what we might call its golden age, rich with star formation, full of bright young stars, alive with supernovae and stellar activity. This age began a few billion years after the Big Bang and will continue for perhaps another trillion years. But that trillion years long, as it seems, is less than 1/10 of the time that red dwarfs will shine. Most of cosmic history, the vast majority of it, will be dark and quiet, illuminated only by the feeble glow of red dwarfs gradually fading away. We can calculate these lifetimes precisely using the physics we've discussed. We know how much fuel a star has its mass. We know how fast it's consuming that fuel, its luminosity. And we know the efficiency of fusion, how much energy is released per gram of hydrogen converted to helium. The calculation is straightforward. Divide the available energy by the rate of energy consumption. The result gives the star's main sequence lifetime. For the Sun, this is about 10 billion years. For Proxima Centauri, 4 trillion. For Eta Carinae, 3 million. But there's a subtlety here. Not all of a star's hydrogen is available for fusion. Only the hydrogen in the core, where temperatures and pressures are high enough, can fuse. In stars like the Sun, the core contains about 10% of the star's total mass. The rest of the hydrogen remains in the outer layers, never reaching conditions suitable for fusion. This limits the fuel supply. Interestingly, low-mass red dwarfs are fully convective. Their entire volume mix is bringing fresh hydrogen from the surface down to the core. This means red dwarfs can eventually fuse all of their hydrogen, not just the core fraction. This is another reason for their extraordinary longevity. Let me share with you a comparison that might help you grasp these timescales emotionally, not just intellectually. If Eta Carinae's lifetime is equivalent to a single human heartbeat, about 1 second, then the Sun's lifetime would be almost an hour, and Proxima Centauri's lifetime would be more than 18 days. All those heartbeats, all that time in the ratio of 1 second to an hour to 18 days. The same process as fusion of hydrogen to helium played out over such vastly different spans. Or consider this, since Eta Carinae formed about 3 million years ago, it has witnessed the entire evolution of the human genus. Homo habilis, Homo erectus, Homo neanderthalensis, and Homo sapiens, all evolved during this star's brief life. If Eta Carinae could observe Earth, it would have seen continents shift, ice ages come and go, and the rise of a technological species. And yet, from the star's perspective, this is its complete existence from birth to death. Meanwhile, Proxima Centauri, having already lived for 485 billion years, has seen the Earth form, life arise, evolve through countless forms, and produce human civilization. And to Proxima, this is barely the beginning. It's not even 1,000th of the way through its life. The psychological impact of these timescales is worth contemplating. We live our lives in decades. Nations rise and fall over centuries. Civilizations last millennia. Even our species has existed for only a few 100,000 years. The timescales of stars dwarf all of this. The sun will outlast any human institution, any human artifact. Even if we survive as a species or evolve into something else, even if we spread across the galaxy, the sun will be here burning steadily long after we're gone. And then there are the red dwarfs, which will outlast not just humanity, but the sun itself, the Milky Way as we know it, perhaps even the last vestiges of galactic structure in the cosmos. Does this make our lives meaningless? I don't think so. Rather, it places us in context. We're temporary patterns in a universe that operates on time scales beyond our comprehension. But we're also rare. We're complex, conscious, capable of understanding those very time scales that dwarf us. A red dwarf will shine for trillions of years, but it will never know it. We can know it. We can look up at Proxima Centauri, that faint red point of light, and understand its past and its future. That understanding is precious, perhaps unique in our corner of the galaxy. As you rest here tonight, breathing slowly, feeling your heartbeat, remember that you're connected to these stellar time scales. The calcium in your bones was forged in a star that lived and died billions of years ago, before the sun even formed. That star's lifetime was short, but it accomplished something. It created elements that would eventually become part of you. You're made of dead stars, yes, but you're also the universe's way of knowing itself, even for a brief moment. Yet stars don't just sit passively burning their fuel in isolation. They interact with their environment, sending out winds of particles that shape the space around them, that affect planets that carry the star's influence far beyond its visible surface. Right now, as you breathe in and out, the sun is breathing too. Not with air, but with plasma. Every second it exhales 1 million tons of charged particles into space, a wind of protons and electrons rushing outward at speeds up to 500 miles per second. This invisible river flows past Earth, past Mars, past the outer planets, creating a bubble in interstellar space that extends 3 times farther than Neptune's orbit. We live inside the sun's breath. And when this breath becomes turbulent, when the sun exhales too forcefully, the consequences ripple across the entire solar system. This stellar wind, invisible to our eyes, but fundamental to the space environment around every star, shapes worlds and protects life in ways we're only beginning to understand. If these explorations of invisible cosmic forces bring you calm understanding, please subscribe and like. Your engagement means the world to this work. The concept of stellar wind wasn't always accepted. In the 1950s, most astronomers believed that space beyond Earth's atmosphere was essentially empty, a perfect vacuum between planets. Then, in 1958, physicist Eugene Parker proposed something radical. The sun's corona, that million-degree outer atmosphere, must be continuously expanding outward. The corona is so hot that its particles move fast enough to escape the sun's gravity. Parker calculated that this outflow must be constant, not sporadic. The sun doesn't just occasionally eject material, it continuously streams plasma into space. Parker's idea faced significant resistance. When he submitted his paper to the Astrophysical Journal, the referee rejected it, calling it impossible. The journal's editor, Subramanian Chandrasekhar, whom we've mentioned before, read the paper himself. Chandrasekhar couldn't find any mathematical errors, so he overruled the referee and published it anyway. Within a few years, NASA's Mariner 2 spacecraft on its way to Venus directly detected the solar wind, confirming Parker's theory. In 2018, NASA launched the Parker Solar Probe, naming it after Eugene Parker, the first time NASA had named a spacecraft after a living person. Parker attended the launch. He was 91 years old and had lived to see his controversial idea become the foundation of heliophysics. Let's understand what drives this wind. The sun's corona, as we discussed earlier, is extraordinarily hot, reaching temperatures of 1 to 3 million degrees Kelvin. At these temperatures, particles move at speeds of several hundred kilometers per second. The sun's gravity, strong as it is, can't hold on to all of them. Particles in the outer corona have enough kinetic energy to escape. As they leave, they create a partial vacuum, and more particles flow outward to fill the space. The result is a continuous outflow, the solar wind. The solar wind isn't uniform. It varies in speed and density depending on where on the sun it originates. The slow solar wind, which travels at about 400 kilometers per second, comes from regions near the sun's equator and from closed magnetic field structures. The fast solar wind, reaching 750 kilometers per second, emerges from coronal holes regions, where the sun's magnetic field lines extend out into space rather than looping back to the surface. These coronal holes appear dark in X-ray images of the sun because they're cooler and less dense than surrounding regions. They're like windows in the corona through which particles can stream freely. The density of the solar wind by the time it reaches Earth is incredibly low. At Earth's orbit, the solar wind contains only about 5 to 10 particles per cubic centimeter. Remember, that's a near-perfect vacuum compared to Earth's atmosphere with 10 billion particles per cubic centimeter. And yet, this tenuous wind carries significant energy and momentum. The total mass loss from the sun through the solar wind is about 1 million tons per second. That sounds enormous, but it's minuscule compared to the sun's total mass. At this rate, the sun will lose only about 0.01% of its mass over its entire 10 billion year main sequence lifetime. The solar wind carries with it the sun's magnetic field frozen into the plasma. This creates the interplanetary magnetic field, a complex structure that spirals outward from the sun like water from a rotating lawn sprinkler. The field lines are drawn out by the solar wind and bent by the sun's rotation, creating what's called the Parker spiral. Near Earth, these field lines make an angle of about 45 degrees to the radial direction. This spiraling magnetic field affects how cosmic rays, high-energy particles from outside the solar system, penetrate into the inner solar system. It provides a kind of shield deflecting some of the most dangerous radiation. When the solar wind reaches Earth, it encounters our planet's magnetic field, the magnetosphere. This interaction creates a bow shock, much like the shock wave in front of a supersonic aircraft. The solar wind compresses the magnetosphere on the side facing the sun and stretches it into a long tail on the night side. Most of the solar wind flows around Earth deflected by the magnetic field, but some particles become trapped in the magnetosphere, accumulating in regions called the Van Allen radiation belts. Under normal conditions, this interaction is relatively quiet. But the sun isn't always calm. It has an activity cycle, the solar cycle, lasting about 11 years. During solar maximum, the peak of this cycle, the sun's surface is covered with sunspots and solar flares, and coronal mass ejections become frequent. A coronal mass ejection, or CME, is a massive eruption of plasma and magnetic field from the sun's corona. A single CME can hurl billions of tons of material into space at speeds up to 3,000 kilometers per second, far faster than the normal solar wind. When a CME hits Earth's magnetosphere, the effects can be dramatic. The increased pressure and the CME's embedded magnetic field can transfer energy into the magnetosphere, accelerating particles to high energies. These energetic particles spiral along Earth's magnetic field lines toward the poles, where they collide with atoms in the upper atmosphere. These collisions excite the atoms, causing them to emit light, creating the aurora borealis and aurora australis, the northern and southern lights. The aurora is literally the solar wind made visible cosmic particles painting light across our sky. But CMEs can cause more than beautiful light shows. Severe space weather can disrupt satellites, interfere with GPS signals, and damage power grids. The most famous example is the Carrington event of September 1859. British astronomer Richard Carrington was observing sunspots when he witnessed a massive solar flare, a sudden brightening of the sun's surface. About 17 hours later, the associated CME reached Earth. The auroras were so bright that people in the Caribbean could read newspapers by their light at midnight. Telegraph systems across North America and Europe failed some, even delivering electric shocks to operators. Telegraph paper caught fire in some offices. If a Carrington-level event occurred today, the consequences would be far more severe. Our technological infrastructure is vastly more complex and vulnerable. A direct hit from a major CME could damage transformers and power grids, potentially causing blackouts lasting weeks or months. Satellites could be disabled or destroyed. Communication systems from cell phones to the internet could be disrupted. In 2012, a Carrington-class CME erupted from the sun, but missed Earth passing through the orbit, where Earth had been just a week earlier. We were lucky. Space weather forecasting has become a serious discipline. Satellites like the Solar Dynamics Observatory continuously monitor the sun, watching for flares and CMEs. When a CME is detected, scientists can calculate whether it's heading toward Earth and when it will arrive. This gives power grid operators, satellite controllers, and airlines time to take protective measures. It's cosmic weather prediction, and it's becoming increasingly important as our society grows more dependent on space-based infrastructure. The solar wind doesn't just affect Earth. It interacts with every planet in the solar system. Mars, lacking a strong global magnetic field, receives the solar wind directly on its upper atmosphere. Over billions of years, the solar wind has stripped away much of Mars's atmosphere, transforming it from a warmer, wetter world into the cold desert we see today. Understanding the solar wind's role in this atmospheric loss is crucial for understanding Mars's climate history and its potential to harbor life. Venus, on the other hand, has no intrinsic magnetic field, but has such a thick atmosphere that it creates its own induced magnetosphere. The solar wind interacts with Venus's upper atmosphere, directly stripping away particles, but at a much slower rate than at Mars. Jupiter and Saturn, with their powerful magnetic fields, create enormous magnetospheres that dwarf Earth's. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear 5 times the size of the full moon. Beyond the planets, the solar wind continues outward, gradually slowing, as it expands into an ever larger volume of space. Eventually, at a distance of about 90 to 100 astronomical units, roughly 3 times the distance to Neptune, the solar wind slows below the speed of sound. This boundary is called the termination shock. Here, the solar wind becomes subsonic and turbulent. Beyond the termination shock lies the heliosheath, a region where the solar wind continues to flow outward, but is no longer supersonic. And finally, at about 120 astronomical units, we reach the heliopause, where the pressure of the solar wind equals the pressure of the interstellar medium. This is the true boundary of the solar system, the edge of the sun's influence. Both Voyager 1 and Voyager 2 have crossed the heliopause, entering interstellar space. Voyager 1 crossed in August 2012, and Voyager 2 followed in November 2018. Their instruments detected the transition clearly: a sudden drop in solar wind particles and an increase in cosmic rays from outside the solar system. The Voyagers are now in interstellar space, but they're still gravitationally bound to the sun, still technically part of the solar system. They won't reach the outer edge of the Oort cloud, the spherical shell of comets surrounding the solar system, for another 30,000 years. The sun's stellar wind isn't unique. Every star has one, though the properties vary. Hot, massive stars produce powerful stellar winds driven by radiation pressure. The photons streaming outward from these stars push on atoms in the stellar atmosphere, accelerating them to speeds of thousands of kilometers per second. These winds are so strong that massive stars can lose significant fractions of their mass over their lifetimes. A star like Eta Carinae might lose several solar masses of material through its stellar wind before it explodes as a supernova. Cool red giants and supergiants also have substantial stellar winds, though the mechanism is different. These winds are driven by pulsations and dust formation. As material in the outer atmosphere cools, dust grains can condense. These grains absorb starlight and are pushed outward by radiation pressure. The gas is dragged along with the dust. Red supergiants like Betelgeuse are surrounded by vast shells of material lost through stellar winds, shells that glow faintly in infrared light. The stellar winds from massive stars shape the interstellar medium in dramatic ways. When a hot star's fast wind collides with surrounding gas, it creates a bubble, a cavity of hot, low-density plasma surrounded by a shell of compressed gas. These bubbles can be tens or even hundreds of light years across. Multiple stars in a star-forming region can create overlapping bubbles, Swiss cheesing the interstellar medium. These structures influence where and when new stars can form, as the compressed shells can trigger collapse in adjacent clouds. For planets, stellar winds are both a blessing and a curse. A moderate stellar wind, like the Sun's, helps protect planets from cosmic rays and can strip away excess atmospheric gases, potentially making planets more habitable. But a stellar wind that's too strong, like those from young or massive stars, can erode planetary atmospheres, entirely making planets less habitable or uninhabitable. The balance matters. We exist on a planet orbiting a star with a stellar wind that's just right strong enough to provide some protection, but not so strong as to strip our atmosphere. Have you ever wondered how the solar wind was first studied before a spacecraft? Scientists measured it indirectly by observing comets. A comet has two tails when it's near the sun: a dust tail which curves slightly due to the comet's orbital motion, and an ion tail which points directly away from the sun. The ion tail is pushed by the solar wind. By studying the shape and behavior of comet ion tails, astronomers inferred properties of the solar wind decades before spacecraft could measure it directly. Nature provided the instrument. We just had to learn how to read it. As you lie here preparing for sleep, you're surrounded by an invisible wind, the breath of our star washing over Earth, carrying with it magnetic fields and charged particles, creating auroras and shaping our space environment. This wind has blown for billions of years and will continue for billions more. It's been here longer than life on Earth, longer than the oceans or the continents. And it will be here long after we're gone, the sun's exhalation continuing in the dark. But stellar winds, profound as they are, represent only the outward flow from a living star. Eventually, every star's fuel runs out. The fusion stops. The balance breaks. And what happens next transforms the star entirely, returning its substance to the cosmos in one final extraordinary act. On the night of February 23, 1987, a light arrived at Earth after traveling 168,000 years through empty space. This wasn't ordinary starlight. It was the death scream of a massive star, a supernova explosion so violent it briefly outshone an entire galaxy. For the first time in almost 400 years, humans could see a supernova with the naked eye. Supernova 1987A taught us something profound. Death in the cosmos is not an ending, but a transformation. When a star dies, it doesn't simply vanish. It returns its treasure to the universe, scattering elements across light years of space, seeding future generations of stars and planets, and eventually life itself. Every atom in your body, heavier than helium, was forged in a dying star. You exist because stars know how to die beautifully. If this perspective on cosmic cycles brings you peace, I invite you to subscribe and like this video. Thank you for being here. Let's begin with what happens when a star like our Sun exhausts its hydrogen fuel. After about 10 billion years of steady fusion converting hydrogen to helium in its core, the core runs out of hydrogen. fusion stops. And when fusion stops, the outward pressure that has been balancing gravity for billions of years disappears. The core contracts under its own weight. As it contracts, it heats up just as it did during the star's initial formation. The temperature rises until it reaches about 100 million degrees Kelvin. At this temperature, helium itself can fuse. 3 helium nuclei combine to form carbon through a process called the triple alpha process. It's called this because helium nuclei are also called alpha particles, and 3 of them are needed. This process was worked out by Edwin Salpeter in 1951 and refined by Fred Hoyle in 1954. Hoyle realized that the triple alpha process should be impossible at the temperatures in stellar cores, unless carbon has a very specific excited state, a resonance that makes the reaction much more likely. He predicted this state before experimenters had found it. When nuclear physicists searched, they discovered Hoyle's resonance exactly where he said it would be. This is one of the most remarkable predictions in nuclear physics, made not in a laboratory, but by thinking about how stars must work. When helium fusion begins in the core, the star's structure changes dramatically. The core, now fusing helium into carbon, is surrounded by a shell where hydrogen is still fusing into helium. The energy from both fusion zones causes the star's outer layers to expand enormously. The star becomes a red giant, its radius swelling to perhaps 100 or 200 times its original size. If the sun became a red giant today, its surface would extend beyond Earth's orbit. Our planet would be consumed, vaporized in the star's outer atmosphere. But despite this expansion, the surface cools. The same amount of energy spread over a vastly larger surface area means lower temperature per unit area. This is why red giants are red. They're cool, at least on the surface, only about 3,000 to 4,000 degrees Kelvin compared to the sun's current 5,500. The core, meanwhile, is hotter than it's ever been, but the surface is cooler. This inversion hot core and cool surface characterizes the red giant phase. For a star like the sun, the red giant phase lasts about 1 billion years. During this time, the star pulsates, expanding and contracting in a regular rhythm. It also develops a strong stellar wind, losing mass at a rate perhaps 10,000 times faster than during its main sequence lifetime. This wind carries away a significant fraction of the star's mass. By the time the sun exhausts its helium fuel, it will have lost perhaps 30 to 40% of its original mass. Eventually, the helium in the core runs out. For a star of the sun's mass, this is the end of fusion. The core isn't massive enough to reach the temperatures needed for carbon fusion. The core contracts one final time, but now it's supported not by thermal pressure, but by electron degeneracy pressure, the quantum mechanical effect we mentioned earlier. The core has become a white dwarf, an Earth-sized ember, with a mass about half that of the original star, cooling slowly over trillions of years. The outer layers of the star, no longer supported by fusion, drift away into space, pushed by the stellar wind and radiation pressure. These ejected layers form a planetary nebula, a glowing shell of gas expanding around the white dwarf. The name is misleading. Planetary nebulae have nothing to do with planets. They were named by William Herschel in the 1780s because through his telescope they appeared as round greenish disks, somewhat like the planet Uranus that he had discovered. We now know they are the shed outer layers of dying stars. Planetary nebulae are among the most beautiful objects in the cosmos. The Ring Nebula in Lyra, the Helix, Nebula in Aquarius, the Cat's Eye, Nebula in Draco. Each one is a star's final masterpiece, a sculpture in glowing gas. The nebulae shine because the white dwarf at the center emits intense ultraviolet radiation, which ionizes the surrounding gas. Different elements emit different colors. Hydrogen produces red light. Oxygen produces blue-green. Nitrogen produces red. Sulfur produces red. The interplay of these colors creates the nebulae's intricate structures. These nebulae are not just beautiful, they are crucial to the chemical evolution of the galaxy. The gas they return to the interstellar medium is enriched with carbon, nitrogen, and oxygen elements created by fusion in the star's interior. This enriched material eventually becomes part of new molecular clouds which collapse to form new stars and planets. The cycle continues. Death feeds birth. But for stars more massive than about 8 solar masses, death is far more violent. These stars have cores hot and massive enough to fuse carbon into heavier elements. Carbon fuses to form neon and magnesium. Neon fuses to form oxygen and more magnesium. Oxygen fuses to form silicon and sulfur, and silicon fuses to form iron. Each stage of fusion requires higher temperatures and lasts for a shorter time. Carbon burning might last 600 years. Neon burning lasts 1 year. Oxygen burning lasts 6 months. Silicon burning, the final stage, lasts only 1 week. At the end of this process, the star has an onion-like structure. The core is iron. Surrounding it are shells, where silicon, oxygen, neon, carbon, helium, and hydrogen are burning in concentric layers. And then fusion stops. Iron is the most stable nucleus. Fusing iron doesn't release energy. It consumes energy. There's no way for the star to continue extracting energy through fusion once its core is iron. Without fusion, without the outward pressure, it provides the iron core collapses catastrophically. In less than a second, a core the size of Earth compresses to a sphere 20 kilometers across. The density becomes so extreme that protons and electrons are forced together to form neutrons. The entire core becomes a giant atomic nucleus, a neutron star, the densest form of matter we know short of a black hole. A teaspoon of neutron star material would weigh 1 billion tons on Earth. The collapse releases a staggering amount of gravitational energy, more energy than the star has produced through fusion over its entire lifetime. Most of this energy emerges as neutrinos, ghostly particles that stream away at nearly the speed of light. But about 1% of the energy goes into the outer layers of the star, launching them outward at speeds of tens of thousands of kilometers per second. The star explodes. It becomes a supernova. For a few weeks, a single supernova can outshine an entire galaxy of billions of stars. At peak brightness, a supernova can emit as much light as the sun will emit over its entire 10 billion year lifetime. If Betelgeuse exploded as a supernova tonight, it would be visible during the day, bright enough to read by, at night a new star suddenly appearing in one of the most familiar constellations. It would remain visible to the naked eye for months. Supernova 1987A. The explosion I mentioned at the beginning occurred in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way. The progenitor star called Sanduleak 69°262 was a blue supergiant with about 20 solar masses. On February 23, 1987, light from the explosion reached Earth. But about 3 hours before the optical light arrived, detectors in Japan, the United States, and Russia detected a burst of neutrinos. These neutrinos, traveling at nearly the speed of light and passing through matter almost without interaction, arrived first. They had left the star's core the instant it collapsed. The light generated in the explosion's outer layers took 3 hours longer to reach the surface and begin its journey to Earth. The detection of neutrinos from SN 1987A was revolutionary. It confirmed our understanding of core collapse supernovae. The number of neutrinos detected, about 20 in total, from 3 different detectors, matched theoretical predictions. It was the first time neutrinos from an astronomical source other than the Sun had been detected, and it opened a new window on the universe neutrino astronomy. Supernovae do more than create neutron stars and spectacular light shows. They forge elements. In the extreme conditions of a supernova, explosion temperatures reach billions of degrees. Neutrons flood the environment. Rapid neutron capture, the R process, builds elements heavier than iron. Gold, platinum, uranium. All the elements that can't be made through steady fusion in a star's core are created in these moments of violence. The gold in any jewelry you wear, the uranium powering nuclear reactors, the iodine in your thyroid all were forged in supernova. But supernovae aren't the only source of heavy elements. In 2017, astronomers detected something extraordinary: gravitational waves from the collision of two neutron stars. Follow-up observations across the electromagnetic spectrum revealed a kilonova, an explosion about 1,000 times brighter than a nova, but not as bright as a supernova. This kilonova created huge quantities of heavy elements, including gold and platinum. Some scientists now believe that neutron star collisions, not supernovae, are the primary source of the heaviest elements in the universe. The expanding debris from a supernova creates a supernova remnant, a bubble of hot gas expanding into the interstellar medium. The Crab Nebula. The remnant of a supernova, observed by Chinese and Arab astronomers in 1954 AD, is one of the most studied objects in astronomy. At its center is a pulsar, a rapidly spinning neutron star that emits beams of radiation. As the pulsar rotates 30 times per second, these beams sweep past Earth like a lighthouse beam, creating pulses of radio waves and visible light. These remnants can persist for tens of thousands of years, expanding and eventually merging with the interstellar medium. They inject energy into the galaxy, creating turbulence, triggering new star formation by compressing molecular clouds. The shock waves from supernovae may have triggered the collapse of the cloud that formed our own solar system 4.6 billion years ago. Radioactive isotopes found in ancient meteorites, isotopes that decay quickly and could only have been created in a supernova, suggest that a stellar explosion occurred nearby just before the solar system formed. Not all massive stars become supernovae. The most massive ones, above about 25 solar masses, may collapse directly into black holes without exploding. The entire star, including its iron core and all the layers above, simply disappears behind an event horizon. These failed supernovae are hard to detect because they don't produce bright explosions. We know they exist because we've observed massive stars that simply vanish from the sky, fading away over a few months without a supernova. There's a profound lesson in stellar death. Nothing is wasted. The hydrogen and helium from the Big Bang were transformed into heavier elements in stellar cores. When stars die, they return these elements to space. Nebulae from dying stars and ejecta from supernovae mix with the interstellar medium. New molecular clouds form incorporating these heavier elements. New stars and planetary systems form from these enriched clouds. Each generation builds on the last. The universe becomes more complex, more rich in chemical diversity over time. Consider what this means for you personally. The calcium in your bones was created in a star that exploded billions of years ago. The iron in your hemoglobin was forged in a supernova. The oxygen you're breathing right now was exhaled by a dying red giant. You are not separate from this cosmic cycle. You are part of it. Your very existence required the deaths of multiple generations of stars. You are quite literally stardust, contemplating stardust, a way for the universe to know itself. And this cycle continues. The stars visible in tonight's sky will someday die. Some will fade quietly to white dwarfs. Others will explode as supernovae. And from their remains, new stars will form, perhaps accompanied by new planets, new chances for life to arise and wonder at the cosmos. The cycle has no end, or rather its end is so distant, so far in the future, that it's beyond imagining. For trillions of years, stars will continue to live and die, each one contributing its substance to the next generation. This is not the ending of the story. It's the eternal present, the continuous transformation that characterizes the living universe. And understanding our place in this cycle, recognizing that we're made of stellar remnants and will someday return our atoms to the cosmos, connects us to something far larger than ourselves. Take a deep breath. Feel the oxygen filling your lungs, traveling through your bloodstream, feeding every cell in your body. That oxygen atom, the one you just inhaled, has a story spanning billions of years. It was born in the core of a massive star, perhaps 20 times the sun's mass, that lived fast and died violently 5 billion years ago. For millions of years, that star fused lighter elements into heavier ones, building up oxygen in its core. When the star exploded as a supernova, your oxygen atom was hurled into space at thousands of miles per second. It drifted through the galaxy for eons, eventually becoming part of the molecular cloud that collapsed to form our solar system. It was locked in rock, released by geological processes, liberated by photosynthesis. And now, right now, it's inside you, keeping you alive. You're not just in the universe is in you. If this journey through stellar science has brought you wonder and peace, please subscribe to continue exploring the cosmos together. Your support means everything. Let's take a moment to truly grasp what we've discovered across these past hours together. We've journeyed from the birth of stars and ancient nebulae to their quiet or spectacular deaths. We've seen how fusion lights the cosmos, how layers of stellar material transform energy, how forces balance in perfect equilibrium, how colors reveal temperature and composition, how time scales dwarf human comprehension, how stellar winds shape space, and how death itself becomes rebirth. But what does all of this mean for us, for you, lying here in the darkness, breathing slowly, preparing for sleep? It means that you are intimately, physically connected to the stars. This isn't poetry, though. It's poetic. This isn't metaphor, though. It's beautiful. This is literal scientific fact. Every atom in your body, except hydrogen, was created inside a star. Let's trace the journey of just a few specific elements that make you who you are. The carbon that forms the backbone of every organic molecule in your body. The carbon in your DNA, in your proteins, and the neurotransmitters firing in your brain. Right now, that carbon was created through the triple alpha process in a red giant star. 3 helium nuclei fused together in conditions of extreme heat and pressure. When that star died, it gently released its carbon into space through stellar winds and planetary nebulae. Billions of years later, that carbon became part of you. The nitrogen that makes up the amino acids in your proteins, the building blocks of your muscles, your organs, your very structure. That nitrogen was also created in stars through the CNO cycle. It too was returned to the cosmos when its parent star died. The oxygen you breathe, as I mentioned, came from massive stars that fused helium into carbon and carbon into oxygen. These stars ended their lives in supernovae, scattering their oxygen across light years of space. The calcium in your bones, giving them strength and structure, was forged in stars, even more massive stars, that achieved temperatures high enough to fuse silicon into calcium. The iron in your hemoglobin, the molecule that carries oxygen in your blood, that iron was created in the cores of dying massive stars in the moments before they exploded. Iron is the end of the fusion chain, the most stable nucleus, and it requires extraordinary conditions to form. And then there are the trace elements equally crucial to your existence. The iodine in your thyroid gland regulating your metabolism, the copper that helps your nerves transmit signals, the zinc that's essential for your immune system. All of these were created either in supernovae or in the collisions of neutron stars. The gold in any ring or necklace you might own was forged not in Earth's crust, but in one of these violent cosmic events when temperatures reach billions of degrees and neutrons were slammed into atomic nuclei. Now consider the hydrogen in your body, the most abundant element in the universe. This hydrogen has an even older story. It wasn't created in stars at all. It was created in the Big Bang itself, 13.8 billion years ago, in the first few minutes after the universe began. The hydrogen atoms in the water, molecules in your cells, in your blood, in your tears, those atoms are nearly as old as time itself. They've been part of interstellar clouds, other stars, perhaps other worlds, and now they're part of you. Think about what this means. You are not separate from the cosmos, observing it from outside. You are the cosmos observing itself. You are a temporary pattern, a brief organization of stellar material that has gained consciousness that can think and feel and wonder. Carl Sagan expressed this beautifully when he said, "We are made of star stuff. We are a way for the universe to know itself." But even this profound statement doesn't capture the full weight of it. You are not metaphorically connected to the stars. You are literally, physically, chemically made from them. The atoms in your left hand probably came from different stars than the atoms in your right hand. You are a collection of stellar remnants, pieces of dozens or hundreds of different stars that lived and died over billions of years, their materials mixing in the interstellar medium, eventually coalescing in the molecular cloud that formed the sun and planets, and ultimately becoming arranged in the specific pattern that is you. And here's something that should fill you with awe: those atoms will continue their journey after you're gone. The calcium in your bones will someday be released back into the earth, where geological processes might eventually return it to space through volcanic activity or asteroid impacts. Billions of years from now, when the sun becomes a red giant and vaporizes the earth, your atoms will be scattered into space once more. They might become part of a new molecular cloud. They might be incorporated into new stars, new planets, perhaps even new forms of life. You are not just made of star stuff. You will become star stuff again. The cycle continues. Let's look up at the night sky together in our minds. When you look at stars, you're looking back in time. The light you see left those stars years, decades, centuries, or even millennia ago. The light from Proxima Centauri, our nearest stellar neighbor, took 4 years to reach Earth. When you see it twinkle in the sky, you're seeing it as it was 4 years ago. The light from Betelgeuse left that star 48 years ago. When you look at Betelgeuse, you're seeing the Renaissance, the age of Columbus and Leonardo da Vinci, written in starlight. But it's even more profound than this. When you look at a star, you're not just seeing its past, you're seeing your own past. That star, or stars like it, created the elements in your body. When you look at the night sky, you're looking at your ancestors, not your biological ancestors, but your atomic ancestors, the stellar forges that created the very substance of your being. And this connection goes both ways. The stars are not cold, distant objects indifferent to your existence. Your existence proves that stars have succeeded in their cosmic purpose to create complexity, to forge heavy elements to make possible the emergence of planets and life and consciousness. You are the proof that the universe is not sterile and dead. You are the universe's way of caring about itself, of asking questions, of seeking meaning. There's a particular moment in cosmic history that's worth contemplating as you prepare for sleep. About 4.6 billion years ago, a molecular cloud in our region of the galaxy began to collapse. This cloud was enriched with heavy elements from previous generations of stars. As it collapsed, most of the material fell into the center, forming the sun, but about 1% remained in a rotating disk around the young star. This disk was turbulent, chaotic. Particles collided, stuck together, building up larger and larger bodies. Dust grains became pebbles, pebbles became boulders, boulders became planetesimals, and planetesimals became planets. One of these planets, the third rock from the sun, had just the right combination of properties. It was at the right distance to have liquid water. It was large enough to hold an atmosphere, but not so large that it became a gas giant. Its orbit was stable, circular enough to provide consistent conditions. And crucially, it was made from material rich in heavy elements, elements created in dying stars. On this planet in the oceans, chemistry became complicated. Molecules formed that could copy themselves. Natural selection began to operate. Life emerged. Over billions of years, that life became more complex. Single cells became multicellular organisms. Simple nervous systems became brains. And eventually, one species developed a brain complex enough to ask questions. Where do we come from? What are we made of? Are we alone? You are the current answer to billions of years of cosmic evolution. You are what happens when stars die, and their remnants organize themselves into patterns capable of thought. The universe spent 13.8 billion years preparing the conditions for your existence. Hundreds of stars lived and died to create the elements in your body. The formation of the solar system was necessary. The emergence of life was necessary. Billions of years of evolution were necessary. All of this, the entire history of the cosmos, was required for you to be here right now, breathing slowly, listening to these words, contemplating your place in the grand story. Does this make you insignificant? Some people fear that contemplating cosmic scales diminishes human importance. If we're just atoms temporarily arranged, if the universe is vast beyond imagining, and we occupy such a tiny corner of it for such a brief time, doesn't that make our lives meaningless? I would argue the opposite. Your existence is so improbable, so dependent on such a precise sequence of cosmic events that it borders on miraculous. You are not insignificant. You are extraordinarily rare. Consider the specific chain of events required for your existence. The Big Bang had to occur with exactly the right properties to create a universe that could form stars. If the fundamental forces were even slightly different, atoms couldn't exist. Stars had to form, live, and die in multiple generations to create heavy elements. The molecular cloud that formed the sun had to be enriched with these elements. The solar system had to form with a planet in the habitable zone. Life had to emerge on that planet. Evolution had to proceed through countless steps, surviving multiple mass extinctions. Your specific lineage had to survive. Every single one of your ancestors had to successfully reproduce. And finally, you had to be born. The probability of all of this happening is astronomically small. And yet, it happened. You are here. You exist. And you have the capacity to understand the process that created you. That's not insignificance. That's profound significance. As you lie here preparing to let go of consciousness for a few hours, to drift into sleep, remember that sleep itself is a cosmic phenomenon. Your circadian rhythms, your sleep-wake cycles are tuned to the rotation of Earth, which is tuned to its orbit around the sun, which is tuned to the gravitational dance of the solar system. You are not separate from the cosmos. Even in your most intimate biological functions, you're connected to astronomical processes. Your brain, the most complex structure we know of in the universe, is made of stardust, organized in such a way that it can reflect on its own origins. The neurons firing in your brain right now, creating thoughts and memories and emotions, are doing so through electrochemical processes involving sodium, potassium, calcium, all elements forged in stars. Consciousness itself, that mysterious quality of subjective experience, emerges from stellar matter. And when you dream, when your sleeping brain creates vivid experiences untethered from external reality, you're demonstrating one of the universe's most remarkable properties, its ability to simulate itself, to create internal models of reality. You are the universe's way of imagining alternatives, of exploring possibilities, of asking, what if? The stars we've explored in these hours together, from their birth in nebulae to their deaths in planetary nebulae or supernovae, they've been doing more than just shining. They've been creating. They've been building the periodic table one element at a time. They've been enriching the galaxy with the raw materials for planets and life. They've been preparing the cosmos for complexity, for consciousness for you. And this process continues. Right now, as you breathe and listen, stars are being born in the Orion Nebula and countless other stellar nurseries across the universe. Massive stars are exploding as supernovae, scattering their newly created elements into space. Red giants are gently releasing their enriched outer layers. Neutron stars are colliding, forging gold and platinum. The cycle of stellar life and death continues, and it will continue for trillions of years into the future, long after our sun has died, long after Earth has been consumed, long after any trace of human civilization has vanished. But right now, in this moment, you are here. You are part of the story. You are the universe's current experiment in consciousness and self-awareness, in the ability to contemplate existence itself. And that is beautiful. That is meaningful. That is worth honoring as you drift towards sleep. Let your breathing slow. Feel your body relaxing. Know that you are safe here in this moment, cradled by Earth's gravity, protected by its magnetic field, from the solar wind, warmed by the sun's light, that traveled 8 minutes from the stellar core, where it began its journey thousands of years ago. You are part of an unbroken chain connecting the Big Bang to this present moment, and from this present moment forward into an unimaginably distant future. The stars will continue to shine, the universe will continue to evolve, and the atoms that currently make up your body will continue their cosmic journey, perhaps someday becoming part of something new, something we cannot imagine. But for now, for this brief moment in cosmic time, those atoms are arranged as you. And that is extraordinary. Thank you for joining me on this journey through the heart of stars, through the depths of cosmic time, through the connections that bind us to the universe. I hope you found peace in understanding these vast processes, comfort in knowing your place in the cosmic story. Your curiosity, your willingness to explore these ideas is itself a manifestation of the universe's drive toward greater complexity and understanding. As you drift towards sleep, carry with you this knowledge: you are made of stars. You are connected to everything, and your existence, however brief in cosmic terms, is a remarkable and meaningful part of the universe's ongoing story. Rest well knowing that the same forces that govern stars also flow through you. The same elements that light the cosmos also animate your body. You are not separate from the wonder you've been contemplating. You are the wonder itself. Sweet dreams, fellow stardust. Until we explore together again, may you rest in the knowledge of your cosmic connection, your stellar origins, and your place in this beautiful, evolving universe. There are always more stories to tell, more wonders to discover, more connections to explore. I'll be here when you're ready to journey deeper into the cosmos. Sleep peacefully among the stars.